In the previous lessons, we learned that most of the atoms on the periodic table are not stable because they don't have a complete valence electron. And in the process, of course, one would gain electron and then the other one would lose electrons. And together they have the opposite charges, and we call this type of interaction called ionic bonding. Then we also talk about how atoms doesn't want to give up its entire electron or have enough energy or have enough power to take an electron from somebody. And in the process, we have a partial positive and we have a partial negative. And this type of interaction occurs in a covalent bonding. And in the process, we have single bond, double bond, and lastly, triple bonds. Okay? Now, that is happening within the molecules. This force happens in a molecules. And that particular force is called intramolecular force. So intra is within a molecules. Okay? Now today we are looking at a larger picture and we look at how those molecules interact with each other. How do we have a molecules of water become a large amount of water all held together in a way that we can actually see and actually drink. So today we are focused on the force between molecules, and the prefix for between is inter. So today we are talking about the intermolecular force between molecule forces. And we are going to look at the different types of intermolecular forces to determine the properties of that particular substance. For example, here is an example of hydrochloric acids right there. And of course, this would be a molecules. And this would be a single bond. And this is intramolecular force, where we also have chlorine with a delta negative right here. It is also attracted to another molecules of hydrochloric acid, where the negative end attracts to the positive end. And that happened throughout the whole entire solution, or in this case, liquid chlorine. And then over here we have pure water. The same thing, right? We have intramolecular force happen again. And here, this would be your intermolecular force. It is happening between molecules. It's the force between molecules that hold them together. So keep that in mind. Know the difference between intra, that's within the molecule, versus inter, between molecules. And the two forces can be described by these two equations. One equation is electrostatic. We are talking about the charges. Okay? And then electrostatic force is very similar to the gravitational force. That's the same force that's holding a planet together. If there is no gravitational force, there wouldn't be any planet, there wouldn't be a solar system at all. All the planets would be going crazy and going different places. So now, with this two formula, or two equation, we can actually understand how molecules actually want to be close together or attract together. So let's compare these two forces, okay? First of all, we know that electrostatic forces, think of electricity, we talk about charges, is happening between the two charges. This is represented by right there. Those are charges. Okay, talking about positive and negative. And the word product right here, the product of the individual charges, that is referring to multiplying or multiply. That's the word product, multiply. And we can see that Q1 multiplied to Q2 divided by the separation distance square. So here we see D right there. That is your distance right there. Okay, and square, that is to the power right there, square. And one thing we need to realize that if the overall force is negative, that means the answer is negative, right? If F is equal to a negative number, the negative force indicate that it is an attractive force. That means the two particles with the two charges attract together. Now let's look at gravitational. Well, in this case, think of the planet or think of object. Well, the planet's a little bit too big, right? But we can see that it is happening between two objects, and every object has a mass. And of course, the term product in math represent multiplication. So we multiply. And it is multiplied between the two masses or the masses of two objects. The same thing, it is divided by the distance square. So d is your distance. And square, that's mean to the power 2. The same thing again, the negative force indicate that the two objects are attractive together, understood to be attractive, okay? So when we have talked about the differences between electrostatic force versus gravitational force. And also one thing that we need to realize about electrostatic force and what makes it special is that when we use the charges, we also have positive and negative. Where the object for masses, we just have the mass in gram, right? Well, in this case, electrostatic force has positive and negative. What happens when you take a positive number and multiply by a negative number? We would equal to a negative number. And in this case, it makes sense. Remember the force negative right here is equal to attractive. So it makes sense opposite charges attract. So we have to realize that proves that a negative values indicate it is an attractive force. But what happens when we have a charged particles with positive charge and then a positive charge, or a negative with a negative? So in this case, we take a negative time a negative, that will give us a positive, or a positive time a positive give us a positive. And that tells you a positive is talking about the repulsive. What does that mean, repulsive? Repulsive, we're talking about repel. And what does the word repel mean? They will push away from each other. Where attractive mean they will push toward each other. They get together. This one, they're moving apart. Now let's look at how the two equations are similar. Well, we know right away that both of them is relative to the distance. And we're talking about the inverse of distance. So what does it mean inverse? That means if the force it go up, the values of the distance will decrease. It makes sense. The closer you are, the stronger the attraction you become. But if the distance get larger, guess what happened to the force? The force is gonna get smaller and smaller. It makes sense. Then another thing that we have to realize that both forces are proportional to the product of the quantity that causes the force. And charges in the case of electrical force, mass in the case of gravitational force. What does the word proportional mean? That means if one go up, the other one also go up. If the other one go down, the other one also go down. So if we increase the charges, okay, guess what happened to the force? It's also increased as well. The same thing for going the other way around. If the charges get smaller, guess what happened to the force between them? It gets smaller as well. And one last thing is that gravitational force is only attractive. It's talking about two objects, how they attract together. Where electrostatic force, or specifically electrical force, okay, either case, electrostatic. Just keep it at the same. How about that? Cross out electrical. Put electrostatic force. Can be either attractive or repulsive, which means like charges repel. Now let's talk about how do different strength of electrical forces, again, this can be used as electrostatic. Between particles actually determine the property of substance, such as the melting point. Melting, what does melting mean? If you have a solid and it would melt into liquid. Okay? And then we have boiling. And boiling, basically, when you have a liquid, it becomes gas. Think of the word boils. When you boil a liquid, it becomes gas. And then it's also affect the vapor pressure and the surface tension as well. We're going to talk about vapor pressure and surface tension later. But for now, let's talk about melting point, boiling point. And in ionic solid, and basically ionic solid are held together by electrostatic attraction of ions. And ions are the one with the positive charges and negative charges. So ions are opposite charges in a lattice structure. Well, what does the word lattice mean? Lattice is talking about repeated pattern of positive, attracting negative, and then this one be negative. In a way, you have this crystal structure that look like crystal lattice, alternating structure of the same pattern. And this pattern continue to exist until it gets so large that we can see with our naked eyes. Think of table salt, right? Think of table salt. It is in the lattice structure because the attraction between the positive and negative charges is so strong in ionic bonding, you would have ionic compound being solid at room temperature. What does that mean? If it's solid at room temperature, that tells you it's going to take a lot of energy to melt this substance. And therefore, it has a very, very high melting point as well as boiling point. And that's the reason why when we try to cook salt, right, when you try to heat the salt substance, it would not turn into a liquid easily. And if you notice, the electron are fixed in that specific area. It doesn't move anywhere. It gets stuck in that bond. We use the term localize. Basically, the electrons are localized. That means they do not move anywhere. They do not move from one end of the substance to another end of the substance. The electron here do not move over here. It doesn't work like that when it's in a solid form. Well, we can actually melt the salt if we have enough energy. We're talking about hundreds and hundreds of degrees. And what we can do is we can melt the salt or any ionic compound. Because it's molten, think of liquid, right? It's actually moving from one end to another end. Now, it's actually electron allowed to move, more specifically, the positive charge. Because it is molten, the ions are now free, so it actually allows us to have the positive charges move from one end and the negative charges move in different ends randomly. And in the molten state, you can actually see ionic compound conduct electricity. So ionic compound do not conduct heat unless, that means you have to, it is molten. And that's liquefied by heat. Right below, we have metallic metals. Strong, but not as strong as ionic substance. And metallic metal consists of stationary positive charges, cores of metal or a metal. And then surrounding that is basically you have positive, and surrounding this stationary positive, we have free-flowing electron. Stationary means you don't move, you just stay there. But free-flowing means you are constantly moving. So in this case, what is free-flowing? Electron. So because electron are allowed to move from one place to another place, you know right away this thing will conduct electricity. And again, what's the opposite of localized? We have the word delocalized. D means not localized. So therefore, if it's not localized, that means it's freely to move. And what's so beautiful about this is that when electrons are allowed to move, it is now conduct electricity. And basically, electricity is a flow of electron. That's all it is. Or flow of charges particles. So in this case, metals are very good conductor. And another properties of metal is that it is very malleable and is ductile. Well, the best example of the word malleable means it could be hammered into shape. Look at the case of this laptop. It is mostly metal. And how is that possible? because we hammer the piece of metal into this shape. Now, to use this laptop, you need the chargers, right? And what's in the chargers? Well, we have wire. Now we have the term ductile. Basically, you can stretch a piece of metal into wires. And because metal are held together by this flow of electron, it is actually very strong. And that's why you see metals are very hard and some are very soft, but they are very strong. And then, of course, they would have high melting point and high boiling point. But still, it is not as strong as ionic compound. Now we are going to look at a more complicated intermolecular force. And all of them are dealing with covalent bonds. But before we talk about the intermolecular force between covalent compounds molecules, we have to realize that within a molecules, triple bond are stronger than double bond, and double bond are stronger than single bond, okay? Because the stronger the bond you have, the harder it is to break the molecules apart. One of the strongest intermolecular force between covalent compounds is network bonds. And this is a specific type of intermolecular force, okay, that's dealing with covalent bonds. Now, network bonds are held together also in a lattice of covalent bonds. The same thing, lattice are basically repeated structure held by opposite charges, okay? Think of ionic substance. They are held together by a very strong intermolecular force. Guess what? This is the same thing. This is the strongest intermolecular force between covalent molecules. And therefore, it will have a very, very high melting point. That means it takes a lot of energy just to melt the substance from solid to liquid, or boiling point from liquid to gas. Now, it's the same thing in terms of ionic compound. Because these are held together in a lattice, the electrons are actually localized. What does that mean? They do not move. And when they do not move, they are very poor conductor. That means they don't conduct electrons. And some example of network solid are basically compounds of carbon. Think of diamonds. Oh, beautiful diamond. And then we have graphite. That is the same substance that you use to write on a piece of paper. Your lead. Lead is actually graphite. Okay? Then we also have compound of silicons, which including quartz. And think of quartz as like crystal structure. Those beautiful crystal. As beautiful as diamond. Okay. One type of intermolecular force between covalent substances is dipole forces that occur between polar covalent molecules. Well, we're talking about molecule with a dipole moment is considered polar. Guess what happened to this name? It was dipole and dipole. We're talking about polar and polar molecule that is attract together. And basically how it works is that the positive ends of one polar molecules is attract to the negative end of another molecules, because opposite charges attract and they just oriented automatically from positive to negative. And of course, the molecule with the greater polarity will have a greater dipole attraction. That means they will held together very strong, okay? And if they held together very strong, therefore they have a very high melting point and high boiling point. Well, overall, dipole attraction are very weak, relatively weak. And because they are so weak, at room temperature, they are usually gases and liquid. And that's the reason why if we have hydrogen chloride or hydrochloric acid, it is usually liquid at room temperature. And that tells you they also have low melting point and low boiling point. It is so low that at room temperature it's either become liquid or gas. However, there is a specific type of dipole forces called hydrogen bonding forces. And this is, again, is a type of intermolecular force, okay? There is a specific type of dipole forces. That means between polar and polar molecules, okay? Now, what makes this so special? It is special because this particular intermolecular force only happens when you have a positive charge hydrogen in one molecule, and it is attracted to a negative charged atom in another molecule. But here's the tricky part. This particular negative charged atom must be fluorine, oxygen, or nitrogen. And the reason hydrogen bonding force is a lot stronger than normal dipole-dipole force is because, remember, hydrogen only has one electron. So when a hydrogen atom gives up its only electron, all the positive charges in an atom will be exposed. And we have exposed positive charge, of course, it's going to increasing the charge of positivity, right? It will attract to a very electronegative. That means you have higher charges of negative and higher charges of positive. Of course, the attraction will be greater. The greater the positive charges and negative charges, it will attract stronger. And that's the reason why it's unique. And that's the reason why hydrogen bonding forces is a lot stronger than dipole-dipole forces. Now, because it is stronger than most dipole and dipole forces, it would of course has higher melting point and boiling point than normal dipole-dipole forces. So, most importantly, they would remain as liquid most of the time at room temperature. And of course, at room temperature, water, what is it? It is liquid. If it's not liquid, we would not be able to drink it. And most importantly, we have one of the most weakest intermolecular force of all. And this force is called London dispersion force, also known as the van der Waals forces. Now, what makes the London dispersion force unique is that this very weak forces between molecules. It is happening in all molecules. It doesn't matter if it's ionic, it doesn't matter if it's covalent, it is happening in all molecules. So London dispersion is happening along with other intermolecular forces. And it doesn't matter what type of molecule it is. All molecules will have the London dispersion, including nonpolar or polar, okay? And this is due to the random motion of electron. Remember, we're talking about electron might be delocalized, but it's moving so fast, it's still moving. It doesn't stay there like a piece of rock and stay there. It's moving back and forth, like vibrating back and forth in that little area. That would be localized. But for delocalized, it would be everywhere, okay? So keep that in mind. And that's the difference between localized versus delocalized. But there is still a random motion. And this random motion of electron is enough for molecules, even nonpolar, to attract together. And again, this is the weakest intermolecular force. It is even weaker than normal dipole-dipole forces. Now, of course, if it's so weak, we would expect that it would have very low melting point and boiling point. And that's the reason why most of these substances are gases at room temperature. For example, methane gases, CH4. For example, methane. This is the gas that we use to cook at home. And one thing we need to be careful about talking about London dispersion is that even though it's weak, but what happens is that this force will increase by a lot when you have a larger substance. That means the larger the substance is, the stronger the London dispersion force will be. So keep that in mind. When comparing different substances, we look at the London dispersion force basically by looking at the molar mass. And basically the London dispersion intermolecular force between molecules actually increase with increasing molar mass. Well, what does mean increasing molar mass? That means the bigger the molecule is. For example here, we have this molecules compared to this molecules. For example, we have these two molecules right here. This one right here is actually C4H10, okay? And then we have a larger molecules. This is C8H18. And because the intermolecular force is a lot larger, and if you notice the two molecules, this one is a lot larger. It has a lot more electrons, right? And it turned out this force is so strong that now you can actually see the difference in terms of their boiling point. And because octane is a lot larger, it has more electron, it's actually boiled at 125 degrees Celsius. C4H10, it's actually boiled at -5 degrees Celsius, which is a lot less. So this is a summary of intermolecular force and how each of them determine the properties of different substances.